Okay, so we have seen classical free electron theory and the limitations of classical free electron theory, and then came the free electron theory, which includes Fermi-Dirac statistics and quantum mechanics, and have discussed the applications of this new free electron theory, which incorporates quantum mechanics and Fermi-Dirac statistics. Now we will discuss about energy bands, how the energy bands originates in metals, semiconductors and insulators, etc. So how this arises? So we were discussing about classical free electron theory and Fermi gas free electron model, where the electrons are moving freely inside the crystal lattice. So in our theory, in our free electron model, the electrons which are moving inside the crystal lattice are very free to move inside the crystal lattice. So actually, whenever the electrons are moving inside the crystal lattice, they are experiencing a potential and a large negative potential actually. I will explain it how, because suppose imagine this is the crystal system or metal system, which will be crystalline. So the atoms will be arranged periodically inside this system. If in a metal system, the valence electrons are free to move inside this lattice. So whenever these electrons move inside this lattice, what will happen? These are electrons. If these are electrons moving inside this lattice, this will be the positive ion cause of the respective atoms. So whenever these electrons are moving inside this crystal lattice, they experience a large negative potential when they reach the positive ion cause, because this is negative charge and this is positive charge. So they will experience a large negative potential whenever they reach the positive ion cause, and between this no potential, and when this electron reach here, it will again experience a large negative potential, and between these two positive ion cores no potential, and whenever it reach this positive ion near the positive ion cores, it again experience a large negative potential, and so on. So when the free electrons are moving inside this crystal lattice, they are experienced by a large negative potential by the positive ion cores of the metal system. The nature of this potential is periodically varying. Why it is periodically varying? Because this is a large negative value. The potential is large negative value here, but zero in between, and again a large negative value here and zero in between. So this is periodically varying. A large negative value, if this is the reference axis, a large negative value here and zero in between these two positive ion cores, and again a large negative value here. Now again this will experience a zero potential in between these two positive ion cores and a large negative potential here, and so on. So the nature of the potential experienced by the electrons moving in the crystal lattice is periodically varying. So the electrons which we are considering, the free electrons, are not completely free but only nearly free electron. Okay, so the nature of this periodic varying potential is very important, and which will which is the and that is the reason for the origin of bands, energy bands, the metals or the solids. So we will discuss the difference between this free electron and nearly free electron model. In the free electron model, the conduction electrons move in a region of constant potential. So, in the free electron model, we are considering the electrons are completely free to move. So, such that there is no potential experienced by this electron. So, it is experienced by a, so in that model, it is moving through a constant potential period. So, this is the reference axis. So, this is the periodic lattice where these are positive ion cores separated by a distance a. So the electrons are moving in a constant potential. Whereas in nearly free electron model, the conduction electrons move in a region of periodically varying potential. So that the electrons are experiencing large negative potential near the positive ion cores and zero potential between these two positive ion cores. Zero because there is no potential contributing factor in between these two positive ion cores. It experiences potential whenever it moves through the near the positive ion cores. So I have explained this just before. So this is the periodic nature of the potential. And the second difference is the lattice is treated as finite, bounded by the surface of the crystal, as the electrons can't go outside the surface of the metal crystal. The potential energy outside the boundary is taken as infinitely large. Inside the lattice, the constant potential of the electron is redefined as zero potential energy by the change of reference value. So in the free electron model, it is treated as a bounded crystal system with finite boundaries. So potential outside the boundary is taken as infinitely large, and inside the lattice the potential energy of the electron is redefined as zero potential energy. So this is shown in figure. So this is the boundary 0 and L, and inside this the potential is 0 and outside it is infinity. So the constant potential we are treating as a zero potential by changing the reference value. So potential energy for linear lattice of length L, U is infinity for x less than or equal to 0, that is outside this region, and at 0 and less than 0, and at L and greater than L. This in potential is infinity, and inside it is treated as 0 instead as a constant potential. Okay, and what is the case in nearly free electron model? The lattice is treated as infinite. By the change of reference value, the potential energy at the sides of the ion cores is taken as 0, and that in between ion cores is taken as a large positive value. So how this is explained? So I can explain this as follows. So we have shown in figure, this is the reference value, and these are positive ion cores distribution. So we have drawn this periodically varying potential as this. It is 0 in between positive ion cores and large negative potential as near the positive ion cores. So this figure is changed to this figure by changing the reference value. What does this mean? This means we are shifting the here this periodically varying potential reference is just shifting to the outside. That is, this figure, this potential is all this, the reference value of this potential is changing. So this figure can be drawn as, so we are changing the reference value, so this figure is and with an approximation. So sorry, not at exact value, in between, and that is, this value is just shifted to upper side and like this. So we have changed the reference. So this is like, suppose you are sitting in your classroom. If we are measuring the height of the ceiling from the ground floor, instead of the floor where you are sitting, the height of the ground floor is measuring, height of the ceiling of your classroom is measuring from the ground floor. So it is so the reference point is the bottom side or the floor of the ground floor. Now if you are changing the reference value or shifting the reference value to your classroom floor, that is to the first floor, so what we are doing is just shifting or lifting up the reference value so that we will get the periodically varying potential of this type as explained in this figure. Okay, so we have down here the periodic lattice. So we have drawn here the width of this potential as, this is 0 and this is minus b and this is a, etc. So this distance will be a plus b and this distance is a minus b. Okay, now so u is equal to 0 for x between minus b and 0. U is equal to u0, not 0, sorry, u0. So the negative large negative potential now is shifted to a constant positive potential by changing or shifting the reference value. So this is u0, 0 constant. So between minus b and 0, this value is u0, and u0 is equal to 0 for between 0 and a. Between 0 and a, this potential is 0. So that is the reference value or shifting the reference value. Okay. Now the third difference is fixed boundary conditions. So fixed boundary condition says x is equal to 0 at x is equal to, psi is equal to 0. The wave function is 0 at x is equal to 0 and x is equal to L. As the electrons cannot go outside the crystal boundaries, psi is equal to 0 for x less than or equal to 0 and x greater than or equal to L. Then for psi to be constant at boundary, psi is equal to 0 there alone. So this is the boundary condition. The electrons can't go outside the boundaries. So psi is equal to 0 for x less than or equal to 0 and greater than or equal to L. And what is the condition in nearly free electron model? The periodic boundary condition is psi of x is equal to psi of x plus t. So the potential is periodically varying in nature. So psi of x is equal to psi of x plus t, where t is equal to n into a, where n is equal to 1, 2, 3, etc. for a lattice of periodicity a. We will explain it here. that is psi of x is equal to psi of x plus na. Okay, so these are the difference between the free electron model and nearly free electron model. Now, connecting this, we have to discuss the Bloch theorem. This is an important theorem. Bloch's theorem states that the eigenfunctions of the Schrodinger function for a periodic potential are the product of a plane wave e to the power I k dot r and a function uk of r which is having a periodicity of the crystal lattice. These eigenfunctions are called Bloch functions. That is, the eigenfunctions of the Schrodinger equation for a periodic potential, that is, which is psi k of r, represented by psi k of r, are the product of a plane wave e to the power I k r. It's the product of the plane wave e to the power I k r and a function uk of r and a function uk of r. And what is the particularity of this function? Which is having a periodicity of the crystal lattice. So this function is a periodic function and its periodicity is equal to the periodicity of the crystal lattice. So this function can be represented as uk of r as uk of r plus t, where t is the periodicity of the crystal lattice. Okay. So psi k of r is known as Bloch function, which is represented in the form like this. So this is the Bloch theorem. Now the proof of this Bloch theorem for the non-degenerate wave functions. So for this, consider a ring of n identical lattice points. We are considering n identical lattice points in the form of rings. Here there are n lattice points, identical lattice points with lattice periodicity A. Lattice periodicity A means the separation between each lattice point is A. The potential energy is periodic in A. So the potential will be periodic in A means that this is periodically varying in this between these lattice points. So periodic in A, and so u of x can be written as u of x plus n into A. Okay, so there are so that means this potential is varying. The periodicity is the periodicity of the lattice is the periodicity of the potential itself. So this is the period of this crystal lattice A. So this is A, 1A, and this is if this is the reference point, this is A and this is A, this is A, all these separation are A. So A represents the periodicity. So the distance from C, if we are taking this point as reference, so the separation between this is A, and from this to this second lattice point is 2A, and from this to this is 3A, etc. So the periodicity, so the the function u of x can be written as u of x plus na. Here we are considering the one-dimensional problem. That is why we are taking it as u of x plus n into a. Because if there are n number of, so for this psi 1 of u1 of x is equal to u of x plus a, and u2 of x is equal to u of x plus 2a, and u3 of x is equal to u3 of x plus 3a, etc. x plus 2x plus 3a, etc. That is why we can write it as u of x as u of x plus n into a. So length of the ring is can be represented as L is equal to N into C. So we have considered a ring of length L, the total length. If we are cutting the ring and stretch it like this, the length of the ring is L. Length of the ring is L, and there are lattice points arranged in this line. So the separation between this period is each lattice point is A, and so if there are n number of atoms, the length of the ring will be L is equal to N into A, because the distance between each lattice point is A, and if there are n number of atoms, the length of this ring will be N into A. Because of the symmetry of the ring, the electron wave function in this lattice should be of the form psi of x plus A is equal to C into psi of x. We have stated the Bloch theorem as for the periodically varying potential, the Bloch function, the Schrodinger equation will obey the Bloch theorem, and it will take the form psi of x plus A as C into psi of A. This is not that. For a periodically varying potential, psi of x plus A will be psi of x. That is, what is the function at a point x will be the same as that at a x plus A, and that will be equal to x, the wave function to psi is at a x plus 2A, and so on. So that's how we are writing this equation like this for a periodically varying potential. So where C is a constant. Now psi of x plus, similarly psi of x plus 2A can be written as C into psi of x plus A. So the function at point A is similar to psi of x at this point is similar to psi of x plus A, and which is again equal to the psi of x plus 2A, and this is again equal to psi of x plus 3A, etc. So we can write it as psi of x plus 2A, psi of x plus A, etc. So instead of psi of x plus A, we can write C into psi of x, so which is C square into psi of x. If it is we can write it as continuously like this. So we can write psi of x plus Na is equal to C to the power N, C to the power N psi of x. Okay. But on the ring, x plus Na and x are the same points, because this is the ring we are considering. Since it is in the ring shape, the point at here, we are starting from here, and we are coming to an end here itself to complete the ring. So this is the starting point and this is the ending point. So psi of x is same as psi of x plus N into A. So this satisfies the condition of function to be single valued, so that psi of x will be equal to psi of x plus N. So we can write psi of x plus N is equal to psi of x. Now this is equation number 2 and this is equation number 3. From these two we can write C to the power N psi of x is equal to psi of x itself, because psi of x plus Na is psi of x. So we can write C to the power N psi of x as psi of x. Now C to the power N psi of x is equal to can be written as e to the power I 2n pi into psi of s, which is, this is 1, so we can write this in the form. So c to the power n is e to the power I 2n pi. C is equal to e to the power I 2n pi by n, where c is one of the n roots of unity. Okay, now I have given here a note. This is just to find the value of k as that we have done in our one dimensional and three dimensional problem of free electron Fermi gas. You just go through it. Now psi of x plus a equation 1 is psi of x plus a is equal to c into psi of x. So psi of x plus a can be written as instead of c we can write e to the power I 2n pi by n into psi of x. So instead of c we have substituted this value. Now consider Bloch function, and so if it satisfy the equation 4, so what we are doing is we have got the wave function or the Schrodinger wave function in the form now by considering the ring of atoms. So we have got this wave function. So we have to consider the Bloch function and have to check whether this function satisfies the Bloch function or it is in the form of Bloch function. If it satisfies, then it is the proof for Bloch theorem. So what we are doing is psi of x is written as uk of x into e to the power ikx. So with k is equal to 2n pi by L, where L is n into a, so this can be written as 2n pi by n into a, and uk of x as uk of x plus na, because u is the potential and which is varying periodically with the period of the lattice. So uk of x can be written as uk of x plus n into a. That is psi of x is equal to uk of x into e to the power, instead of k we are writing in 2n pi by n into a into x. So similarly for psi of x plus a can be written as uk of x plus a into e to the power I 2n pi by n into x plus a. So here we are writing this term first, and uk of x plus a is uk of x itself, and again this we have expanded this bracket, and this a and a cancel in the second term, so that is we have written here, and this is the first term with the x we have written here. Now this term is nothing but psi of x, so we will get psi of x plus a as e to the power I 2n pi by n psi of x. So this satisfies, so this is of the form of Bloch equation, or this wave function satisfies the Bloch theorem. Thus a Bloch function defined by equation 5, that is equation 5 Bloch function. We have defined a Bloch function like this, defined by this equation satisfy the periodicity of the wave function as given by 4. So this is about Bloch theorem. Okay.